Definition for permanent magnet DC motor is the magnets are radially magnetized and are mounted on the inner periphery of the cylindrical steel stator. The stator of the motor serves as a return path for the magnetic flux. The rotor has a DC armature with commutator segments and brush. For basic configuration of a permanent magnet DC motor is very similar to that of a normal DC motor. The working principle of any DC motor is same. Example, when a current carrying conductor is placed in a magnetic field, it experiences a force. A permanent magnet DC motor also works on the same principle. Besides that, the permanent magnet DC motor generally operates on 6 volt, 12 volt, or 24 volt DC supply obtained from the batteries or rectifiers. The interaction between the axial current carrying rotor conductors and the magnetic flux produced by the permanent magnet result in the generation of the torque. Application of permanent magnet DC motor is permanent magnet DC motor are extensively used where smaller power rating are required. For example, in toys, small robots, computer disk, drive, and so on. The objective for our task is first, equivalent circuit and relevant equation. Second, torque speed characteristic. And last, speed control and application, disadvantage or other relevant element.
This is equivalent circuit for permanent magnet DC motor. When we look at the equivalent circuit, where IA is armature current and RA is resistance of the motor, while EB is the back electromagnetic field of the motor and V is the supply voltage. As in the permanent magnet DC motor, the field is produced by a permanent magnet. There is no need for drawing field coil in the equivalent circuit of a permanent magnet DC motor. The supply voltage to the armature will have armature resistance drop, and the rest of the supply voltage is counted by the back electromagnetic field of the motor. Hence, the voltage equation of the motor is given by V equal IR plus EB. Okay, we continue with relevant equation for permanent magnet DC motor. In conventional DC motor, the generated or back EMF is given by the equation shown below. E equal K flux N, equation number 1, and the electromagnetic torque is given as T equal K flux IA, equation number 2. In permanent magnet DC motor, the value of flux is constant. Therefore, the above equation 1 and 2 become E equal K1N, equation number 3, T equal K1IA, equation number 4. Considering the above circuit diagram, the following equations are expressed. V equal E plus IA RA for equation number 5. Putting the value of E from the equation number 3 in equation number 5, we get V equal K1N plus IARA, or N equal V minus IARA over K1 for equation number 6. Where K1 equal K flux and is known as speed voltage constant or torque constant, its value depends upon the number of field poles and armature conductors. The speed control of the permanent magnet DC motor cannot be controlled by using flux control method, as the flux remains constant in this type of motor. Both speed and Torque can be controlled by armature voltage control, armature rheostat control, and chopper control method. These motors are used where the motor speed below the base speed is required, as they cannot be operated above the base speed.
So, for the third objective is torque speed characteristic. Characteristics of Pmdc motors are similar to the characteristic of DC shunt motor in terms of torque, speed, and armature current. However, speed-torque characteristics are more linear and predictable in Pmdc motor. The permanent magnet motor uses a magnet to supply field flux. Permanent magnet DC motors have excellent starting torque capability with good speed regulation. A disadvantage of permanent magnet DC motor is they are limited to the amount of load they can drive. These motors can be found on low horsepower application. Another disadvantage is that the torque is usually limited to 150% of rated torque to prevent demagnetization of the permanent magnet.
Type of permanent magnet materials. There are three types of permanent magnet material used in Pmdc motor. The detailed information is given below. Elnikos. Elnikos has a low comprehensive magnetizing intensity and high residual flux density. Hence, it is used where low current and high voltage is required. Ferrite. They are used in cost-sensitive applications such as air conditioner, compressors, and refrigerators. Rare earths. Rare earth magnets are made of samarium cobalt, neodymium, iron boron. They have a high residual flux and high comprehensive magnetizing intensity. The rare earth magnets are exempted from demagnetizing problems due to amateur reaction. It is an expensive material. Application of the permanent magnet DC motor. The Pmdc motor are used in various applications ranging from fraction to several horsepower. They are developed up to about 200 kW for use in various industries. The following applications are given below. Pmdc motors are mainly used in automobile to operate windshield wiper and washer, to raise the lower window, to drive blower for heaters, and air conditioner. They are also used in computer drive. This type of motor are also used in toy industries. Pmdc motors are used in electric toothbrushes, portable vacuum cleaners, food mixer. Used in a portable electric tools such as drilling machines, head trimmers. Advantages of the permanent magnet DC motor. Following are the advantages of the Pmdc motor. They are smaller in size. For smaller rating, permanent magnet reduce the manufacturing cost and thus Pmdc motor are cheaper. As these motors do not require field windings, they do not have field circuit copper losses. This increases their efficiency. Disadvantages of the permanent magnet DC motor. The disadvantage of the Pmdc motor are given below. Permanent magnets cannot produce a high flux density as an externally supplied shunt field does. Therefore, all Pmdc motor has a lower induced torque per ampere turn of armature current than a shunt motor of the same rating. There is a risk of demagnetization of the pole which may be caused by large armature currents. Demagnetization can also occur due to excessive heating and also when the motor is overloaded for long periods of time. The magnet field of Pmdc motor is present at all times even when the motor is not being used. Extra ampere turn cannot be added to reduce the armature reaction.
This is for our animation permanent magnet DC motor.
In this video, we will logically understand the operation and construction of commercial DC motor. Let's first start with a simple DC motor possible. It looks like this. The starter provides a constant magnetic field, and the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law. So the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connected with the power source of opposite polarity. As it results on the left side of the coil, the electricity will always flow away, and on the right side, electricity always flows toward. This ensures that the torque is also in the same direction throughout the motion. So the coil will continue rotating. But if you observe the torque action in the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nearest zero. As a result, there will be irregular motion of the rotor. If you run such a DC motor, here is the trick to overcome this problem. Add one more loop to the rotor with a spread commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source. So the motor force is always present in the system. Moreover, the more such loop, the smoother will be the motor rotation. In a practical motor, the armature loops are fitted inside slot with highly permeable steel layers. This will enhance magnetic flux interaction. Spring-loaded commutator brushes help to maintain contact with the power source. A permanent magnetic starter pole is used only for very small DC motor. Most often an electromagnetic is used. The field coil. The electromagnetic is powered from the same DC source. The field coil can be connected to the rotor windings in two different ways. Parallel or series. The result is two different kinds of DC motor construction, a shunt and series motor. The series one motor has good starting torque, but speed drops drastically with the load. The shunt motor has a low starting torque, but is it able to run almost at a constant speed, irrespective of the load acting on the motor. Unlike the other electrical machine, DC motor exhibits a unique characteristic. The production of back EMF, a rotating loop in the magnetic field, will produce an EMF according to the principle of the electromagnetic induction. The case of the rotating armature loop is also the same. An internal EMF will be inducted opposite to the applied input voltage. The back EMF reduces armature current by a large amount. Back EMF is proportional to the speed of the rotor. At the starting of the motor, back EMF is too low. Thus, the armature current becomes too high. leading to the burn out of the rotor. Thus, a proper setting mechanism that controls the applied input voltage is necessary in large DC motor. One of the interesting variations of the DC motor is a universal motor, which is capable to run under both AC and DC motor source.